Vivian, did you hear that Carl's gonna join today, or maybe not?
I don't know. I don't think so.
I don't think so. Okay. Okay, great. Yeah, glad he's on vacation day.
Okay, so um, welcome back. And before I start, I just want to make a organizational consideration. I mean, I hope that I cannot always look at the chat. I will try, but generally speaking, just try to speak up, or if there is a possibility in Zoom to ping when someone raises a hand or something like that, that would be ideal, and then I could take questions. But otherwise, just speak up. Okay, so this time we talked about several things, but the first thing in order is a correction. So when I defined the natural numbers, I said that the natural number n is the union of all its previous natural numbers, but this is not true. What should be is it's the set of all previously defined natural numbers. And the confusion, I mean, another way to define n is by saying that it is n minus 1 union the set containing n minus 1. So this is consistent with the way we defined 0 to be the empty set, 1 to be, well, it is the empty set union the set containing the empty set, but any set union with the empty set is just the set itself. So it is this, and then 2 is going to be the set union the set containing the empty set, which is this set. So this is not something we are going to rely on, but still I want to be precise about it. The other things, we talked about injective maps. Injective map. This is a function from A to B, such that for any A different than A prime in A, f of A is different than f of A prime. And surjective is kind of a dual notion. It means that for any B in B, there exists some A in A such that f of A is equal to B. And similarly, you can say that bijective functions is just injective and surjective. Now, we had, I think the last thing we did is a theorem or proposition that if f from A to B is bijective, there exists a function which we denote as f minus 1 from B to A, such that f minus 1 composed f is the identity function on A, and f composed f minus 1 is the identity function on B. So this function f minus 1 is called an inverse to f. But note that the converse is also true. That is, if there exists f minus 1 from B to A such that f minus 1 composed f is the identity of A, and f composed f minus 1 is the identity of B, then f must be f is bijective. How do we see this? This is very easy. So suppose we need to show that f is bijective. That is to say, we need to show that it is injective and that it is surjective. So how to show that f is injective? If I take two different elements, A and A prime in A, I need to show that f of A is different than f of A prime. But what I can do, well, I can take f minus 1 of f of A. This, because f minus 1 f is the identity, this must be equal to A. And f minus 1 of f of A prime must be equal to A prime. So it cannot be that f of A is equal to f of A prime, because f minus 1 is a function. If these two purple elements would be equal, then since f minus 1 is a function, it would have to associate to associate to them the same output. But we know that A is not equal to A prime, so f of A cannot be equal to f of A prime. And similarly, I guess we can put it as an exercise. That in this case, f is also surjective. Now, one thing that is kind of a meta principle, I guess you could say, that notions of types of functions like injective and surjective are what is called closed under composition. And what I mean by that is that if you give me two functions, f from A to B and g from B to C, and both f and g are injective, or both of them are surjective, then G composed F is also of this type. And how to see this? It's very easy. Suppose we go for the injective case. So both functions are injective, and I want to show that the composition is injective. So I take two different elements, A and A prime in A. Then f of A is different than f of A prime, since f is injective. And G of f of A must be different than G of f of A prime, since G is injective. So what we get is that G composed F is injective. And a similar argument, again, you could try it as an exercise, shows that composition of surjective maps is surjective. And of course, if you combine the two statements about injective and surjective, you get that the composition of bijective maps is bijective. Now, before we move on to new material, I want to give it a try and tell you about Cantor's theorem. I guess I forgot to give you the updated notes. So you should see it in the chat. But so this is an aside, which is not something we are going to use, but I think you will find it interesting. And this is called the Cantor's theorem. And what it says is quite simply, there is no surjective map from the natural numbers to the real numbers. Before I go to the proof, are there any questions on what I said so far? Okay, so how does one go about proving that there is no surjective map? This is usually done in a method, I mean, a proof by contradiction. So suppose by contradiction or towards contradiction, that there is some function f from the natural numbers to the real numbers that is surjective. Now, a real number I can represent. I can write in a decimal representation. So what I can do, well, let's denote f of n, the image of the natural number n under f, as xn. Then I can write xn to be x1 index n dot x2 index n, x3 index n, and so on, where x1 n is some integer, and all the rest of the xin, so for any I bigger than 1, xin is a digit. Okay, so if this is the case, now I can order I can basically write f as an infinite table as follows. So I get 1 is mapped to x1, and x1 we said we denote it as x11 dot x21, and here possibly infinite sequence. In fact, we can always say it's an infinite sequence that may end in a tail of zeros. So the same goes for 2. 2 maps to x2, which is x to 1, x to 2, and so on. Then on the nth element, I have xn, which is xn1 dot xn2, and here it goes on. Let's say I can continue it to xnn, and of course it continues after that. So just for symmetry, here I also have x2n, and here I have x1n. Now, I define some element y in R as follows. So y, it has a decimal representation. Let's say y1 dot y2. Here it goes up to yn, for example, and it continues. Y1, I'm going to take it to be x1, 1 plus 1. Y2 is going to be x2, 2. Well, I could do cases, or I could do modulus, but let's say it's going to be x2, 2 plus 1 if x2, 2 is different than 9. And otherwise, I could take x2, 2 minus 1 if x2, 2 is equal to 9. And the same goes for any n. So yn is going to be equal to xnn plus 1 if xnn is different than 9, and xnn minus 1 if xnn is equal to 9. So the picture, and this is why it is called the diagonal argument, I have this infinite table, and now I look at the diagonal. And what I'm doing is I define a number y by tweaking each of the entries in the diagonal of this infinite table. And so note y is not equal to xn for any n. I guess say it like this. For any n, y is not equal to xn, because the nth digit of y is different by definition from the nth digit of xn. Thus, F is not surjective. And that's a contradiction. Any questions about the proof? Hello, I'm not sure I'm not sure I can hear you.
Oh, can't hear you.
Ah, okay. So this is a bit of an advanced topic, but I thought you could digest it, and it has an interesting application for computer sciences. And this is the following example. Choose a programming language. Programming language and consider and let P bar be all computer programs. In this language. Now, I can look at a sub collection of P bar be the set of all programs that print a decimal representation. For example, you can have the program that print 0.3, or let's say it prints 0 point, and then it prints in a loop, let's say while true, print 3. So this is a computer program, a legitimate, it will compile. The issue is that it does not stop, but we can consider so for such a program, P in curly P, the theoretical print output is an element in R. Right? I mean, as if you would, in this example, the theoretical output would be 0.33 and so on, which is, of course, is just a third, is a real number. And now I claim that there exists a real number x that is not obtained as a theoretical output, as a theoretical output of any program. And in fact, there are many such real numbers. So if you think of it, it tells you something about the impossibility of true randomness. And how do you prove it? I can give you a sketch because I get a feeling that you're not completely completely interested. But the way to prove it is you say if it wasn't the case, then for any real number we could write a program whose theoretical or eventual printing output is this number, and this means there would exist a surjective map, let's call it F, from the set of all computer programs that print a decimal representation, this we called curly P, into the real numbers. By assigning for each computer program the theoretical output. So P goes to the output of P. And what it implies, in fact, I can simply define, let's say, F bar from P bar to R by saying that F bar of some P is, let's say, 0 if P does not belong to this F bar of P is 0 if P does not belong to curly P, and it is the output, theoretical output of P, if P does belong to curly P. And this map is also surjective, because the previous map, F, was surjective. Now, the set of all P bar, so furthermore, we can order the set of all computer programs in a given language in a lexicographic order. And this means that I get let's call it G bar. I get a map from the natural numbers to the set of all computer programs in my given language. This, for example, you could do that G of 1 is the program that is simply the string A, up to, what is it, G of 24, 26, forgot. This would be Z. And then G of 20, 25 would be AA. And so on. And this map is clearly surjective. And all of this is to say that now I would get, I have a surjective map from N to P bar. This I call G bar. And I have a surjective map from P bar to R. We call it F bar. And of course, as we said, the composition of surjective maps is surjective. So the map F bar composed G bar from N to R is surjective. And that is a contradiction to Cantor's theorem. I feel that you are not completely the same page. Are there any questions?
I think it's very good, interesting.
Thank you. Yeah, I wasn't sure if that would be of interest to you. I thought it would. I mean, you always hear that true randomness is not possible, but how do you actually prove it? Right. So this is an application of this surjective and injective maps. Okay. So unless we have you have other questions, the next topic I want to discuss is groups, which is certainly relevant to almost anything we do later on. So a group is a set G together with binary operation which I call, at the moment, I call it mu. Binary operation simply means a function from the Cartesian product to G. So the Cartesian product of G with itself to G, and you write it as you take a pair. I mean, the Cartesian product is the collection of all pairs, ordered pairs, and you map it to mu of xy. Here, if I wanted to be formal, I would say mu double brackets xy, because xy comes with brackets as is. And our official syntax for writing a function is that we do the function, brackets, and the argument. But we abuse notation to avoid multiple brackets. We simply write mu xy, and this will happen many times later on. We omit a repetition of brackets to get a clearer, more intuitive notation. Okay, so a group is a set G together with a binary operation and a chosen element. E such that the following conditions are met. One is that for any x in G, if I take the binary operation of x and the element E, I guess you could call it a unit. This is often called unit or neutral element. And if I take the binary operation of x with the unit element, in either side, I get simply x. So this is equal to mu of ex. This condition is called the unitarity. Unitarity. And the second condition is that for any x, y, and z in G, mu of, I guess I need more space. So mu of mu xy with z is equal to mu, to mu of x, mu of y, z. And this is called associativity. And the last condition is the existence of an inverse. So for any x in G, there exists some element which we denote as x minus 1 in G, such that mu of x minus 1 is equal to the unit element E, but also if you do it on the other side, mu of x minus 1, x. Okay, and this is existence of inverse. All right, so let us try to digest this definition. I think you probably saw a definition of a group, but maybe not in this way. It's completely equivalent to the way you to the other definitions you saw, but it's a bit more abstract because I define it in terms of this function mu. But really, what there is here is a meta principle. Algebraic notions, I guess you could even say mathematical notions. Can be described by first giving data. This data is basically, from the axiomatic point of view, is just a collection of sets. And two conditions that this data need to satisfy. So if you think about this meta principle in the definition I gave for a group, you could say that the purple part is the data, and the yellow part is the conditions. And this will repeat in almost all definitions that we give. So of course, this we discussed last time. I mean, here I say that mu is a function, but a function is just can be viewed as a set. And this condition it seems like it may be a condition that is data, but in fact it is, you can say that this is simply the existence of I mean, you could say that I have another function which I call I from G to G, and this function is bijective, and this function needs to satisfy. So mu of x with I of x. Yeah, I'll try to write it here. It's like it's going to be mu of x, I of x is equal to E, and similarly on the other side. So I of x we denote as this we can denote as x goes to x minus 1. Okay, now the convention, any question about the definition? So the conventions in the notations, I am not going to write a mu. It's too cumbersome to write mu all the time. So we write dot instead of mu. But so it means that dot is like is like a function from the Cartesian product of G with itself to G, and we map the pair xy, we write it as x dot y, and sometimes we even omit the dot. So this is the dot notation, but of course, it may be that the binary operation comes from a usual addition or multiplication of numbers. And if it is the case, we will often denote the binary operation as addition or multiplication. And the unit element, if the binary operation was a multiplication of numbers, then usually the unit element is 1. So we will write 1 instead of e. And if the binary operation is addition of numbers, then we will write 0 for the unit element, because this is usually the case. So this is all a bit of a warning, but we will soon see examples. Okay, so but if I don't assume anything on the group, then I have this dot notation instead of mu. So the axioms are 1, that x times e is equal to x, which is equal to e times x. This is for all x in G. 2, that for all x, y, z in G, xy times z is equal to x, y, z. This is what we call associativity. And 3, for every x, there exists x minus 1, every x in G. There exists x minus 1 in G, such that x times x minus 1 is e, which is also x minus 1 times x. Okay, so famous groups. One, I take take an object E, then you take G as a set, it's just the element E. And the binary operation, it's the only possible function that you can define. I mean, E binary operation with itself is E. Right? Note that okay, let me wait for the next example. So this is called the trivial group. Of course, the empty set is not a group, because it does not contain any element. In particular, it cannot contain an element that will be the unit element. A second example is you take the integers with addition and the 0 element. Now, I need to tell you what is the inverse. So inverse of x in z is simply minus x. So you see, when we when we deal with the integers, it is more natural to denote the binary operation as plus, the unit element as 0, and the inverse of x as minus x. So you can think of it like it's the same principle that is both applicable to multiplication and addition. I mean, you have a neutral element with respect to the binary operation, and the inverse of this element is an element such that if you do the binary operation with the so-called inverse, you get the neutral element. So if you have real numbers with multiplication, then the unit element or the neutral element with respect to multiplication is 1. And the inverse of an element x is 1 over x, or what we denote as x to the power of minus 1. Now, note, now I take the natural numbers. It has addition, and it has an element. Let's say I take the natural numbers with 0, and I take addition, and I treat 0 as the neutral element. This is not a group. Can anybody say why it is not a group?
Because there are no inverse elements.
Yes, exactly. It does not contain the inverse of elements, basically of any non-zero element does not admit an inverse. The third example is one that you know. I mean, I take the integers modulo n. This is, you can view it as the set of numbers from 0 up to n minus 1. But the binary operation is, I will write like this, plus mod n. And the unit or the neutral element is 0. So all this stuff is a group. And so if A is an element, then n minus A is going to be the inverse of A. Right? Since if you take the binary operation and you apply it on A and n minus A, you get, well, n mod n, which is equal to 0. So n minus A is the inverse of A. Associativity, you need to check it. But taking modulo n is an associative operation. I will just write the equation that you need to verify. So let's say you have A, B, and C in Z mod n, then you need to verify that if you take A plus B and you do mod n, and then you add C and you do mod n, you get the same thing as you take A and you add to it B plus C mod n, and then you do mod n. This is really the equation. So guess we can put it as an exercise. All A, B, and C. Okay. I think it's a good time to take a break. The next example I want to talk about is kind of a geometric group. But how about we take 10 minutes break?
Yes.
Okay, so see
Yeah,
you
yeah.
soon.
Yeah.
Okay, so the next example, I mean, I want to spend some time on it because it gives you an illustration of the type of object we eventually are going to study, namely elliptic curves. They have, we said that this is a geometric object, like a solution of a certain equation, and it also has an algebraic structure of an abelian group. So consider S1, which is, you know what? I will simply start with the complex numbers. The complex numbers I'm going to write as x plus iy, such that x and y are real numbers. And you can multiply two complex numbers. Let's say z is equal to x plus iy, and z prime is x prime plus I prime y, sorry, iy prime. Then z multiplied by z prime is, you just do the usual multiplication. What you get when you assemble everything is x prime minus y prime plus I xy prime x prime y. Okay, and this is another complex number, but complex numbers you can represent as, if I have z, this is the real axis, this is the so-called imaginary axis, and z has this quantity is, well, if z is x plus iy, then this quantity is x, and this quantity is y, right? This is it's the same as. But you can draw kind of a vector that it takes goes from the origin to the point z, and this vector will create an angle with the positive part of the real axis, or of the x-axis, if you want. And moreover, this this vector will have a length, and call it r. So I could write, in fact, z, well, z is equal to r times cosinus theta plus I sinus theta. Because here, if you do the usual sine and cosine definition, you get that y is r sinus theta, and x is r cosinus theta. And in shortened notation, we write it as r kis theta. And if you examine the multiplication I just defined, and you use some trigonometric identities, you will get that. So if I have z is equal to r kis theta, and z prime is r prime kis theta prime, then when you multiply, the way to multiply is you multiply the radii, r and r prime, and you add the angles. So in slightly more expanded writing, this is r prime times cosinus theta plus theta prime plus I sinus theta plus theta prime. Now, inside the complex numbers, there is the so-called unit circle, which is the set of complex numbers z such that the radius of z is equal to r kis theta, and r is equal to 1. Usually we denote, so if z is r cosinus r kis theta, we will denote by absolute value of z to be the real number r. So I could say simply the circle is the set of all z such that the absolute value of z is r, is 1. Now, if I take 2 points on the circle, z and z prime, each of them creates, has an angle, say theta and theta prime. And when I multiply them, and of course the radius of both of them is 1. So when I multiply z and z prime, what I get is, well, it's a point that has a radius 1, so it must lie again on the circle. And the way I compute it is, I mean, I simply add the angles theta and theta prime. So this would be something like this, where the angle here is theta plus theta prime. This is z prime. And I claim observe, S1 with the multiplication of complex numbers and the element 1 is here, the purple element. This is 1, which is simply 1 plus 0i. Okay, so this, I claim that this is a group. Well, associativity of the binary operation, it follows from associativity of multiplication of complex numbers, which in turn, if you think of it, it simply follows from associativity of multiplication of real numbers. Of course, the unit element 1, it has angle 0. So if I multiply the unit element with any other element, I get this other element. So the unit element is neutral, indeed. And then I need to tell you what is the inverse. So can anybody say what is the inverse if Z is equal to R kiss theta? What is the inverse? We are going to denote the inverse as Z minus 1 because we are in multiplicative notation. But what is the description of Z minus 1? I mean, here Z is equal to R kiss theta, but R is equal to 1, so I just delete R. Can anybody say what is Z minus 1?
Is it negative theta?
Yes, but what is negative theta?
Cis of negative theta. I'm not
Yes,
sure.
but what is negative theta? I mean, the way we defined it, theta must be positive.
Okay, then 360 minus
Yes.
theta.
Yes, and I usually use what is called radians. So 360, I call it 2 pi. So pi is 180, and this and if you take 2 pi minus theta and you multiply it with z, so you take z minus 1, you get a cis of 2 pi, and this is indeed simply 1. Okay, so it's kind of it's a funny case, because the operation is formally speaking, I mean, the operation is multiplication of complex numbers, but in fact, the only thing we do is we add the angles. So this is an example of a group which is also a geometric object. Geometric really means that, well, it can have different meanings, but for example, you can look at it as the set of solutions to the equation x squared plus y squared minus 1. This is the circle. So, okay, but all the examples we did are what is called a group. G is a billion if for any two elements you can do x times y, and this is equal to y times x. And if you think of it, all the examples we saw are a billion groups. In all the examples we saw, the binary operation is commutative. Here is a non-commutative group. Let n be the set of all numbers 1 up to n. And Sn, I take all functions from n to n, such that f is bijective. This is called the symmetric group. Now I need to tell you what is the operation. So maybe we can call it instead of f, we call it sigma. Sigma operation tau is defined to be simply the composition sigma compose tau. So of course, well, we have this this condition that the elements of the group need to be bijective maps, but we had, if you remember, in the first part of this session, we said that composition of bijective maps is bijective. So in fact, this operation is well defined. I mean, you get another element of Sn. And associativity, if you have a sigma, tau, and rho, and you do it like this, this by definition, it's sigma composed tau composed rho. But since composition of functions is associative, you get sigma composed tau composed rho, which by the definition of the binary operation, this is sigma operation tau and operation rho. So this is associativity. And the unit element is the identity function, identity n to n. Of course, if I compose any function with the identity function, I get the other function. And existence of inverse follows from the proposition we said that a bijective map, to say that a map is bijective, is actually equivalent to say that it has an inverse. Inverse in the sense, so inverse of sigma is what we denoted. We also denoted it as sigma minus 1. Exist since sigma is bijective. And this operation is not commutative. It's because composition of functions usually, of course, it could, by some coincidence, it could be commutative, but it usually isn't. So exercise, find sigma and tau, choose an n, such that sigma operation tau is not equal to tau operation sigma. Any questions on that? All right, so for the next example, I would need a theorem which is called Fermat Little theorem. And it goes as follows. If P is a prime, and A is some number between 1 and P minus 1, then A to the P minus 1 is equal to 1, mod P. So here I do multiplication mod P. And the proof, I need a lemma. I need a lemma. So the lemma says, consider what we denoted FP is the set of all numbers from 0 up to P minus 1 with a plus mod P and multiplication mod P. Then for any n and any x, y in FP, x plus y to the P is equal to x to the P plus y to the P mod P. Okay, this is it's like the heaven of equations for beginners. I mean, you don't have to worry about the brackets. You just do you just raise each variable to the power of P. Okay, so there is the so-called a binomial formula. That is, if I take xy times xy times x plus y, and I do it in our case p times, but this formula, of course, is valid for any power you take of x plus y. Then this is equal to the following expression. I write sum I equals 0 to p of p choose I, x to the I, y to the p minus I. This formula is really follows from combinatorics. It is valid in any place you have a multiplication and addition. I mean, basically, because what did I do here? I mean, I mean, if I open these brackets completely, well, I will have an expression, for example, of the form x times x times x to the p. But a generic expression will be you choose either x or y here, then you choose either x or y here, then you choose either x or y here, and you multiply it all together. But what are the options I have? I mean, basically, once I chose I places of x, let's say I chose 3 places of x, and that's all the x's I chose, the rest of them need to be y. So I have now how many options do I have to choose 3 x's out of this p? It's p choose 3. And for each such option, the expression I would get is x to the I times the remainder. I have to have y to the p minus I. So this is a sketch of the proof of the binomial formula, but I think many people get it in the school. Now, this p to the I, sorry, p choose I is a p factorial over I factorial times p minus I factorial. Since p is prime, a p does not divide I factorial, because I factorial is a multiplication of numbers which are all smaller than p. So none of them can really, I mean, p cannot divide it. And also p does not divide p minus I factorial. Because again, it's a multiplication of numbers that are all smaller than p. But p does divide p factorial. And what I get is that as a result, p must divide this expression, p over I. But this is true, of course, if I is not in the edges. So I need to be bigger than 0 and smaller than p. Because if I, for example, if I is equal to p, well, I mean, if I is equal to P, then I get P does divide I factorial, right? For example. So this is all to say, all the inner expressions here, I get that x plus y to the P is equal to, well, now I need to take the sum only with the edges. So I equals 0 and I equals P. When I equals 0, I get x to the 0 times y to the P. I should say, yeah, if P divides P over I, this means that P over I is equal to 0 mod P. So all these expressions here in blue, where I is not 0 or P, they all have a coefficient which is 0 modulo P. So they all vanish. And then I'm left with the coefficients in the, I mean, with the expression, the terms in the edges, which are x to the 0, y to the P, plus x to the P, y to the 0. So this is x to the P, y to the P, but of course this is only true if I do mod P. Any questions about the lemma? The lemma is going to be central in calculus modulo P. Okay, and now I'm going to prove. Now let's prove Fermat a little theorem. Remember, I want to prove that a to the P minus 1 is equal to 1 mod P. So we want for any A between, well, for any A in the set 1 up to P minus 1. But equivalently, I could just say that A to the P is equal to A mod P. So I will prove, we will prove this purple equivalent statement. And we prove by induction. By induction on A. So A equals 1, A equals 1 is clear. 1 to the power of P is 1 modulo P, even not modulo P. So suppose A to the P is equal to A mod P. And now I want to prove it for A plus 1. But A plus 1 to the P by Fermat is A to the P plus 1 to the P. That's Fermat. And by induction, a to the p is simply a. So I get, and 1 to the p, of course, is 1, is mod p. Okay, and this finishes the proof. I mean, we showed by induction that that a to the p is equal to a mod p. Any questions about these two statements? Okay, so now the next example uses these statements. I take, I call it FP star. FP star. This is all the numbers 1 up to p minus 1 with the binary operation being multiplication mod p. And I claim that this is a group. So what the obvious conditions to check is that it is this binary operation is associative. That's very clear because we said that multiplication mod p is associative. The unit element is 1 because we are like in multiplication of numbers. 1 is going to be the neutral element to the binary operation. But what we the non-trivial condition to check is that for any element, any a in FP star, there exists what is called a minus 1, such that, well, a times a minus 1 is equal to 1. Can anybody say what is going to be a minus 1? Hello? This is something you should definitely be able to answer, and it uses the previous propositions we discussed.
Is it a to the p minus 2?
Exactly. Take a minus 1 to be a to the p minus 2. Okay, then a times a minus 1 is a to the p minus 1, which is 1. All right, so this is the example of what is called the multiplicative group of the prime field FP. We will, of course, discuss fields extensively later on, but for now you can see the non-trivial part is the existence of inverses, and for that you really use the fact that P is prime. So everything here in terms of operations could have been defined for any natural number n instead of P, but you will not have this property here in blue rectangle this property will not be true if P is not a prime. And essentially because this argument that all the binomial coefficients vanish modulo P is not true for a natural number that is not prime. So the whole argument collapses, and therefore we really have to have a prime number in order for the for example for this collection to be a group. Any questions? Okay, so suppose H and G are groups. I guess I want to specify the unit elements. So G operation, and I will write operation G to denote that it's from G, and unit element sub G. And the same I do for H. This is just to disambiguate the two terms. And so suppose I am given two groups, G and H. Each of them, it has a unit element, E in one case, E of G, in the other E of H, and it has a binary operation. Then I can consider the Cartesian product, G times H, which I remind you is the set of all X, Y, all ordered pairs, such that X is in G and Y is in H. And on this set G times H, I can define a binary operation. So for X, Y, and X prime, Y prime in G times H, I define XY operation X prime, Y prime to be X operation in G, X prime, Y operation in H, Y prime. And the unit element E of G times H, I simply define as you take E, the unit element of G, and the unit element of H in the second coordinate. This is, of course, an element in the Cartesian product. And I claim that this is a group. Okay. The inverse, of course, if I want to take the inverse of X, Y, what I do is simply the inverse of the element X in G and the inverse of the element Y in H. Exercise. G times H with this operation is a group. So if you want, you can think of it as now we are abstracting one level. That is, with a group, it has like it's something with a binary operation. So in a group, I can take two elements and apply the binary operation to get a new element. But you could also view the collection of all groups. I will write it, this is a bit informal. So the collection of all groups, you take two groups, G and H, and you give it a new group. I mean, G times H. So in fact, you can view this star, I mean, the Cartesian product as a binary operation on the collection of all groups. And note, of course, the number of elements in G times H is simply the number of elements in G multiplied by the number of elements in H. Okay, so I think this is a good place to take questions and finish the session. Are there any questions or comments? Was it too slow?
For me, it was fine. Yeah, it's fine.
Okay, I mean, I don't want to I mean, I don't want to go too slow because then people feel it's a waste of time. But I also don't want to rush. I think it's good to lay down the foundations carefully, and then it's better in the continuation.
Yes, I agree. I think the same. This is the base, and yeah.
Okay, so if there are no other questions or comments, let's finish here, and we see each other next week.